Okay, so let's prove that recursively enumerable and co-recursively enumerable is the same as being recursive. And to prove this, we're going to heavily invoke the Turing thesis by describing a Turing machine by some algorithm, and then claiming because the algorithm exists, therefore the Turing machine exists. Okay? So I'll prove for the forwards direction, and then I'll prove the reverse direction. So the forward direction, we're going to let L be recursively enumerable and co-recursively enumerable. Okay, what does that mean? That means there exists a Turing machine M1 such that if X is in the language, then M1 of X accepts. Okay, clearly, if it's recursively enumerable, then I get this property. Also, because it's co-recursively enumerable, there exists a Turing machine M2 such that it accepts the complement of the language. That is to say, if X is not in L, then M2 of X accepts. Okay, so I've got these two machines, M1 and M2. If I feed X to both of them and I run, suppose I feed X to M1, so what's like a naive approach to building a Turing machine that always halts on all inputs, that recognizes the language L? Well, I guess I'll just feed it to M1, and then if M1 halts, halts and accepts, I'll say yes. And if it doesn't, then I'll ask M2. The problem is M1 might not halt to begin with if X is not in the language. Certainly, X is either in or is not in the language L. That means one of these two guys has to halt, but I don't know which one. So what I can do is I'll run both of these machines in parallel. I'll get a new Turing machine, I'll call it big M. And what this machine will do is it will take in a string X and feed it to both M1 and M2, emulating them in parallel. Well, Turing machines are purely sequential machines, so how do I emulate two machines in parallel? Well, I guess I just emulate one time step of M1 of X, and then I emulate one time step M2 of X, M1 of X, M2 of X, tick-tock, tick-tock, tick-tock. One of these guys has to eventually halt. So by running them in parallel like this time sharing, one of them eventually has to halt. And so depending on what happens, if M1 accepts, then I accept. And if M2 accepts, then I reject. Okay? This formally defines a new machine M, and M has the property, M fed a string X, it's going to accept, it's going to halt and accept if X is in the language, and it's going to halt and reject if X is not in the language. M is always guaranteed to halt because at least one of these two machines is guaranteed to halt. So M always halts for all inputs. By construction. That means because we have a finite decision process that checks for membership of L, that means L is recursive. Okay? Again, we don't have to explicitly construct the machine M that does this property. We can just declare that one exists by like intuitively describing the algorithm. Okay?